One of the things that I also wanted to talk about a little bit, and you alluded to it right at the beginning when you mentioned foundational models, and then what you just mentioned before this, right, which is in terms of being able to abstract the real world well enough to be able to train models and run simulations, is something that I wanted to double click, right? So I think data in particular as a building block is something that I remember always being a challenge, right? In robot training, you have a lot of these platforms. You have NVIDIA with like Isaac Sim, and I think recently they launched something for self-driving called Alpamayo, and their entire effort is, look, how do we actually like abstract the real world? How do we like provide all this like data for physical AI development, which is supposed to be very different, right? I remember when I was starting my first job, I was at a razor blade factory working for P&G, and we were trying to implement um, certain like vision systems to detect defects in razor blade packaging, right? And in another factory, we were trying to like detect any physical damage to the edge of a razor blade after it's been sharpened in a very high speed line, right? These are like lines processing, I think on the lower end, 300 razor blades per minute, at the upper end, 900 razor blades per minute. So it's milliseconds of operation that's happening at every stage of the machine. And it was just impossible, right? Because you had to teach the algorithms back in 2019, 2020, what each individual defect look like, right? Like this is a corner folding, this is a tear, this is an incorrect gluing, right? And so on and so forth. And it became like a nightmare to be able to generate enough quantities of defects, to be able to train the model to understand what is bad quality product and reject it, such that I think the savings that we would get from the machine's uptime improving were completely eroded by the amount of product that had to be wasted to collect enough images to be able to train a functional machine learning model, right? And at that time, this only went so far. Today I understand that in a lot of places where I had seen people implementing these techniques, there are like actual like production scale live solutions, right, that are being able to detect defects in milliseconds, microseconds, and like reject the bad product physically from the machine, right? And similarly on the humanoid robotics side, or what I see folks who I know working in with the warehousing side and material handling, their robots are being able to achieve like millimeter precision in going in, picking up a pallet or picking and placing things and so on and so forth, right? So I want to understand what has become different, what is changing, right, from a data availability, from a data infrastructure perspective. How close, do you think we actually are to achieving that sort of holy grail of endless, completely realistic, synthetic, and like simulated data? But that data bottleneck or that real world or that sim to real gap that you were mentioning, how broad is that gap today and how fast is it diminishing?
Yeah, so there are actually multiple facets to this. So I think firstly, if you talk about endless synthetic data, I think we, arguably speaking, we already have that. If you, with the caveat that it's all endless simulated data, but it's not accurate, right? So, with varying levels of accuracy, I guess. Uh, and by accuracy here, I mean like how realistic is it? How close is it to the real world? So one thing that some people have done is that they're like, hey, look, we don't know the exact, for example, like friction coefficients of the real world in every possible environment. We don't know, like, there are different physical parameters, like, coefficient of restitution, things like that. We don't know all of those in the real world, right? We don't have all the dynamics, right? But what some people say is that, hey, if we train our model in simulation and we train it on so much data with randomized physical coefficients, right? So we randomize, like sometimes we give it a slope, sometimes we give it varying terrain, sometimes we give it, like, if we're talking about, let's take an example of teaching a humanoid robot how to walk, right? So it's like, if we or teaching a some other like four-legged robot dog to navigate something, it's like you can randomize your floor alone in so many ways: terrain, friction, how slippery it is, etc., etc. That um, the hope is that if you randomize it enough, the real world, like if your randomized space is like some spectrum, the real world will always lie within that spectrum, is the hope,
I
right? So
see.
like
I see.
if you go to some carpeted floor, it'll be at one point in the spectrum. If you go on a tiled floor, it'll be at another point in the spectrum. But the hope is that with enough data, you would have um seen the real world, enough of the real world at different points in the spectrum.
And
So
one question just to jump in here
mhm,
because I'm super curious about this. But how do you know, right? Like if you can generate every possible variation
mhm,
of reality using physics, right?
mhm,
And the good part is that the real world is within this superset somewhere. But you
mhm,
want to train the model on the real world, right? In some
mhm.
sense, you don't want it to learn physics which are irrelevant, like which are unrealistic or incorrect in
Yeah.
some shape or form, right? So how do you weed out what is actually real from like a billion, trillion, quadrillion different things that you could simulate? I was just on that point, I was just curious.
Yeah, I no, that's a good question. I think uh the way we usually do it is that is not necessary. Like short answer is we can't weed out, basically, because the problem is that we don't know exactly which parameters are closest to the real world. So we actually don't know. But the good news is that what we do is we make the model perform well in all of those scenarios. So we
I
train
see.
it to perform well in situations which may not be super realistic. Um, but the hope is that if we give it enough data, and this is what people have observed, is that you give it enough data, the model actually see the model is we tend to like humanize the model by saying like, oh, the model learns this and learns that. It's just a
Mhm.
mathematical mapping, right? It picks up patterns from the data based on the objective that you're training it for. So when you give it a lot of data from a lot of different very diverse data, what happens is you remove any other spurious correlations
I see.
that might be in the data. So the only possible thing that the data can so that the model can learn is the real way to solve the problem, which is that,
I see.
okay, if I need to step in this way, I mean, a simple example from like image classification is like, people have observed that with if you train a model on very small data sets, then your model overfits, right?
Right, right.
What overfitting means is that it learns some pattern which is present in your training set, but it's not a real pattern
I
that
see.
exists
I
in the
see.
real world. So it could be, for example, that in your handwritten data set, yeah, whenever you wrote the number 9, some pixels in some particular spot were like there was some noise there or something like that, right? And that's what the model learned. But if you collect like a million or a billion such images, then all such noise disappears over time, because it becomes much more representative of the real, like, images of digits or whatever that you see, or
Right,
letters that you see in the
right.
real world. And um, at that scale, those noise effects tend to average out. And it's the same thing with this domain of randomization that I'm
I
talking
see.
about, which is
I
that
see.
the more you randomize, the more these spurious effects will kind of average out, and you'll force the model to learn what's actually needed to solve the problem. And yeah, this is like kind of this is only step one, I think, in like the what you mentioned about like having endless simulated data.
Synthetic data.
Step
Yeah.
two is like we can make simulated data more realistic. So especially I talked about like randomizing environments. We can't really do that with images, right? Because if you look at images, if you just count like in a 300 by 300 image, there are so many possibilities of pixels. Like, each pixel has 256 values, or 256 to the power of 27. It's like some
It's an
astronomical
absurdly,
number.
absurdly large number. Yes.
Right. So it's not possible to do this for images. So for images, what we do is what you were alluding to, which is we have to weed out non-realistic images. There are lots of different techniques to do that. Generative AI, generative vision models have become a long
Mhm,
way.
mhm,
So
mhm.
they can help you either convert. There are a lot of simulators which render images for you, which are kind of like have realistic physics, but not very realistic appearance. So you have models that can convert them to more realistic looking images. There are models that do physics and video together. So all of that is also like, exploding very, very quickly, like with things like Sora and all these video generation models. So that's the second thing is that we are, I think, in the image space. So on the physics space, you can just randomize everything. In the image space, you can now convert uh, uh, rendered, like not realistic looking simulated images to very realistic looking images.
Right, right,
And I think the way that the most robot learning companies see data now is it's a pyramid. So what I mean by that is data for, and again, this is very similar to LLM pre-training and stuff like that. So for LLM pre-training, what people have found is that, hey, when you pre-train a model from scratch, you just train it on all kinds of data you can get your hands on. So just scrape the internet, just throw in everything that, well, I mean, not everything, but like they still do have some quality checks, but really it's like all as diverse data that you can get your hands on, different languages, different genres, etc., etc. Then the next level is, okay, what people often call SFT, supervised fine tuning, but it's
right.
basically now we focus on very highly curated, very small data sets, like very, very high quality code, for example, for code generation models, or very,
Mhm.
very high quality essays, or very, very high quality question and answering, and things like that. And then we post train this large model on these very small data sets, so that it still remembers the semantics and language and knowledge about the world that it learned from pre-training, but it also it becomes very targeted in its output.
Right, right,
And then
right.
finally, they do like some RL to kind of push it from. So the way I think you can think about it is like very, very roughly speaking, these aren't
Yes.
real numbers, but like pre-training gets you from 0 to 50.
Uh-huh.
Supervised fine-tuning gets you from 50 to 80 or 90. And um, uh, what do you say? RL, like RLHF and all these things get you from 80 or 90 to 100. And it's very similar in robotics now. But I think the biggest question on everyone's mind is we don't know what that pyramid looks like for
I see.
robot learning.
I see.
But roughly speaking, and this is kind of, there's a lot of consensus around this. Most people view like random in the wild videos, like random YouTube videos, make up the bottom of the pyramid, right? They're most easily available, very cheap, but very low quality. Like it could be anything. It could be people like us, like talking. It could be like people actually interacting with the world. Some of that is more valuable than others. Not all of that
Sure.
data is valuable. So figuring out, so that's why it's the bottom of the pyramid. And then top of the pyramid is probably what you were describing, which is, it's called teleoperation, which is that someone like wears a suit or a glove, and whatever they do, the robot mimics their movement. So that's like the gold standard, right? Like if you could have a human do that in like all possible situations, and we collected a massive like internet scale data set of that, like we would be done. So, but it's obviously very expensive to collect. You need a lot of robots, a lot of humans. So that's why it's like at the top of the
One
pyramid.